Okay, so chapter 18 is all about thermodynamics. We've already talked about enthalpy in Chem 110. So enthalpy was the heat of a reaction, the amount of heat released or absorbed from a chemical reaction. But now in this chapter, we're going to introduce two more thermodynamic values, and there are several more than that. But we're going to introduce two more thermodynamic values, one called free energy or Gibbs free energy, and the other one's called entropy. So free energy is exactly what it sounds like. It is the amount of energy free to do work. So the amount of energy that we can get from a chemical reaction that we could actually do work. That's the Gibbs free energy. The entropy is actually a quantified measure of disorder or chaos. So we're going to introduce those new thermodynamic values in this chapter. So again, just as a review from Chem 110, thermodynamics is simply the study of the relationship between heat and other forms of energy in either a chemical or physical process. And of course, we're going to be dealing with the chemical processes. Make sure that you review chapter 9, sections 2, 3, 6, and 10 of your second edition TRO. If you have the first edition TRO, again, there's that paper posted on Canvas that compares the two different books. Okay. So let's talk about what a spontaneous process is. So a spontaneous process is one that occurs by itself. So an example would be a rock rolling downhill. Now, this rock might have started at the top of the hill, and I might have had a pebble underneath of it, and I might have had to kick the rock to get it to started, but once it started, it would roll downhill. That is still a spontaneous process. Just because I had to give the rock a little kick doesn't make it non-spontaneous. Okay? So the fact that the rock rolls downhill is spontaneous, even if I had to give it a little kick of energy, an activation energy, let's say. Get it? Okay? So there's a spontaneous reaction. That rock falls downhill. Examples of chemical spontaneity would be that heat flows from a hot object to a cold one. An iron nail will rust in moist air. Those are spontaneous chemical reactions. Now, the processes occur without recurring any outside force, again, until equilibrium is reached. So again, that's always going to be the idea here, is that when we say the end of a chemical reaction, we're talking about when equilibrium is reached. Non-spontaneous process, as you can imagine, is one that does not occur by itself. It does not mean that it cannot occur. It means that it does not occur by itself. So for example, a rock does not spontaneously roll back up a hill. However, I can do work on that rock and I can push that rock back uphill, but it's going to cost me energy. Heat does not flow from a cold object to a hot one. However, we do it all the time with our air conditioners. Again, that costs us energy. So we can make these non-spontaneous reactions occur, but it's going to cost something. It's going to cost energy. So internal energy, again, as we talked about in Chem 110, is just the sum of the kinetic energy and the potential energy. Now, the kinetic energy is what we call thermal energy or energy of movement. And the potential energy, well, there's a whole bunch of types of potential energy. So this is a total potential energy. Part of that potential energy, of course, is just gravitational potential energy. The higher you lift something up, the further it can fall. So there's the gravitational potential energy. But then we also talked about chemical potential energy. We called that the internal energy in Chem 110, right? Now, we also talked about state functions. And we talked about how this internal energy, again being the chemical potential energy, is a state function. And some of you have heard about the story of Jack and Jill, who went up the hill to fetch a pail of water. Well, it was a really big hill, and they knew that they had to make this trek at like 6 o'clock in the morning. And so the blue trek here is Jill, and the red trek here is Jack. And the night before, Jill went to bed early. She already had all of her stuff packed. She had a compass, GPS. She was ready to go. Jack, on the other hand, had a big party to go to. And so he stayed out till like 5 o'clock in the morning, crawled back home, closed his eye for 5 minutes, and then had to get back up. Came out, had nothing with him, forgot everything, forgot his map. And so they set out, and Jill, with being well prepared, went straight up the side of the mountain. Jack, on the other hand, he kind of stumbled through the woods, losing his way, fell off the side of the cliff. They had to life flight his bloody ass back up to the top. Then on bloody hands and knees, he finally crawled to the top of the mountain. Now, the change in potential energy, how is it different for Jack and Jill? The change in gravitational potential energy. Is it the same or different? Is the change in gravitational potential energy the same or different for Jack and Jill? Kaylee, what do you think?
Is it the same?
Yeah, right. Gravitational potential energy only matters the difference in height, right? So gravitational potential energy is what we would call a state function. The initial and final states, it doesn't matter how you got there. It just matters about the difference. So it makes the math real easy. It's just the final minus the initial. That is the difference in gravitational potential energy in this case. What about work? Did Jack and Jill do the same amount of work? No, right? So work is what we call a path function. A path function requires calculus to determine. Heat is exactly the same way. Jack expelled a heck of a lot more heat than Jill did. So heat is also a path function. It also is going to require calculus to determine its value. So that's the difference between a state function and a path function. State function only depends on the initial and final states. It doesn't matter what path it took to get there. That's important because all the thermodynamic values we're going to talk about, internal energy, enthalpy, entropy, Gibbs free energy, they are all state functions. So we only ever need to worry about the final and initial states, the change in, that's it. Okay, so the change in potential of energy of both Jack and Jill is the same. Okay, because it only mattered between the initial and final positions. Extensive and intensive properties. And an extensive property, simply it matters how much is there, such as mass and volume. An intensive property doesn't matter how much is there, so the Keller, the temperature, the pressure, and any value in which you take one extensive property and divide it by another extensive property automatically makes it an intensive property. Okay, that's just all a review of 110. And we're going to continue our review of 110 here for a while. So we talked about the change in internal energy. And so again, the internal energy is really just the chemical potential energy. That's really what the internal energy is. And again, since it's a state function, all we have to do is take the final minus the initial to figure out what that is. Now, generally, we can't exactly say what the final is or even the initial, right? There's too many factors, you know, because the internal energy has things like, well, bond energies, ionization energies, electron affinities, vibrational energy, rotational energy, electronic excitation energy, and then nuclear energy, right? We could rip the atom apart into its individual subatomic particles. So where does that stop? Well, we don't really know. So what we generally actually measure is the change in these values. So we're going to measure the change in internal energy, the change in enthalpy, the change in entropy, and so on and so forth. Now, the internal energy, again, changes, but we can't create nor destroy matter. So we're going to consider two things. We're going to consider our system. That's generally, in our case, the chemical reaction. that we're interested in, and then the surroundings, which is just basically everything else. So any energy that we lose by our system must be gained by our surroundings, and vice versa. So again, if the system gains energy, it must have gained it from the surroundings. So the surroundings lost energy. When we think of loss, we think of a minus sign. When we think of gain, we think of a positive sign. Okay. So again, now the first law of thermodynamics is actually defined in many, many ways. We defined it once already in Chem 110, is that the change in internal energy was simply the work plus the heat. Okay, so that's one way to define the first law of thermodynamics. Another way to define it, and in the end, okay, that is not spin, that is entropy. I'll get to that. I'm not sure what the S means, or the spin means, but S, it represents entropy. I'll tell you what, I'll come back and address those questions later, and because I don't know what you're talking about at all, to be honest with you. When I get to entropy, let me know if I answer the question that you're asking. I don't understand what spin, why you're talking about spin. Okay. So anyway, so the first law of thermodynamics states that in any process, spontaneous or non-spontaneous, the total energy of a system and its surroundings is constant, right? Again, we can't create nor destroy. Again, we'll get to that. S is entropy. Okay, so these exchanges of energy are of two kinds. They're of heat and work, right? So heat, we're going to give the variable Q, and heat is simply the energy that moves in or out of a system, and that's generally because of difference in temperature, right? And so for a spontaneous reaction, the heat is always going to flow from the one with the higher temperature to the one with the lower temperature. So heat is not a temperature difference. We can calculate the amount of heat that's transferred in or out of a system by using the difference in temperature. We could actually quantify it that way, and you've already seen that, right? We talked about heat capacities in Chem 110 and how the heat in or out of a system was proportional to the change in temperature of that system. The proportionality constant, of course, being the heat capacity of the system. And then there's work. Well, work is simply the energy exchange that results when a force moves an object through a certain distance, right? So we've already said that work is equal force times distance. So that's just our definition of work. Now, all energy, regardless of what it is, has units of joules. So work has units of joules, heat has units of joules. So again, energy just has units of joules. Now, the sign convention of work and heat. Work done by the system is negative, right? So the system had to use up energy to do whatever work, to push whatever it was. In the case of chemistry, that work is usually the molecules pushing against other molecules in the atmosphere or pushing on the walls of the container in which they're in. So if it's doing work, if the chemical reaction is causing work to be done, then the system is losing energy and it's going to be negative. Work done on the system then is going to be positive. Okay? Heat evolved by a system, which we say it's exothermic, is negative because it's losing energy. Heat absorbed by a system, which we call an endothermic process, again, the system is gaining energy, so it's going to be positive. It's absorbing energy from the surroundings. Now, here's an example. Here I have, again, we have this little cylinder, right? And inside we have a gas. And if I heat up the gas, right, we know according to the ideal gas law, PV equals nRT, if I heat up the gas, but the number of gas molecules don't change, then the pressure inside would increase, except that this is a movable piston. And so the pressure is going to remain constant if the external pressure is constant. So that means the volume is going to increase. And when the volume increases, it's going to push up this cylinder with a certain weight. So we're moving, we're causing a force, and we're moving at a certain distance. The force is going to be related to the mass of this weight and the gravitational constant. So that's going to be the force that's being applied. And then, of course, the distance is going to be related to the volume change. Since the diameter isn't changing, it's just going to be the height. Okay, so there it is. We can show that we're doing work on this system. Let me give an example of that. So here we have a similar system, right? In this cylinder, I have some calcium carbonate, and I put it in an acidic solution. And of course, we know that when carbonates react with acids, they produce carbon dioxide gas and water. So the carbon dioxide gas has to go somewhere, so it's going to end up pushing up on the weight, okay? And it's also exothermic, so it gets hot. It's going to release heat. So that means the system is losing energy because it's losing heat, and it's losing energy because it had to do work on this cylinder. Okay, it had to push up on this weight. So we lost energy from both work and heat in this case. Okay, so now again, another way that we can state the first law, the way we did in Chem 110, is we said the change in internal energy is simply equal to the heat lost or gained plus the work done by or on the system. Okay, and again, the sign convention, if the system loses heat, Q is going to be negative. If the system does work on its surroundings, W is going to be negative. So the signs will take care of themselves. Now, in most chemical reactions that don't produce gases and are at constant pressure, basically the internal energy is simply equal to the heat because there's no work being done. Now, keep in mind, I'm going to show you that there's other types of work, like pushing electrons through a wire. Well, that's actually work, okay? Breaking the surface tension of a liquid, well, that's actually work. But in most cases, the change in internal energy is approximately equal to the change in enthalpy. And again, the enthalpy, we called it the heat of reaction, the amount of heat absorbed or released by the chemical reaction, so no work. And again, like I said, but not all. There are definite exceptions to that. So let's actually quantify this. So we got we have our cylinder. We have 0.25 moles of calcium carbonate in it. We have an excess amount of nitric acid. So all the calcium carbonate is going to react to form carbon dioxide gas and water. And we have a constant pressure. So including the atmospheric pressure and the weight, that resulted in a force of 2 atmospheres. Okay, and we have a temperature of 25 degrees Celsius. So we want to quantify the change in internal energy. So when a reaction is run in an open vessel at constant pressure, any gases produced represent a potential source of expansion work. So this is one form of work. So any chemical reaction that produces a gas will produce expansion work. So when gases are produced, they exert force on the surroundings as a pressure, okay? So there's our force times the height, right? So this is just our definition. So there's the downward force. So this is the downward force of the atmosphere plus this little weight combined together represents 2 atmospheres. We got to push against it, right? So we'll have a negative force to push against that to lift this thing. Now there's our height. Okay, so there's the height. Now, of course, we could rewrite this. The height is just going to be the change in volume divided by the area, because the change in volume, right, is just going to be the area of this times the height. I just rearranged that and replaced height then with this, okay? Okay, now I'm going to rearrange S again, and we have the force over the area. Well, force over area is a pressure, okay? So force over area is just a pressure. So I could replace this then with the pressure. So now we have a new equation for work when dealing with expansion work in chemical reactions. And this is the only work we're going to deal with in this class. Okay, so it's going to be expansion work, and it's going to be P, and this has to be at constant pressure. Notice that it's not del P. So this works at constant pressure only. Okay, so we got constant pressure and then the change of volume. It's negative, again, because the system is pushing, it's losing energy. So that's where the negative comes from. Okay, so here's our balanced chemical equation for the calcium carbonate reacting with the nitric acid. Nitric acid, again, is a strong acid. It's going to dissociate into H plus and NO3 minus. The NO3 minus isn't a factor, so it's just the H plus that we're worried about. So that's where the H plus is. It reacts with the hydrogen ion reacts with the carbonate to form carbonic acid, H2CO3, but that, of course, is unstable and breaks down into water and carbon dioxide gas, leaving behind a calcium ion. Okay? So if we want to calculate the work done, well, we know the pressure. The pressure was 2 atmospheres. How am I going to calculate the change in volume? Yeah. Well, how about the ideal gas law? Right? I can simply use the ideal gas law for it. The only thing, if the pressure is remaining constant, the temperature is remaining constant, molar gas constant, of course, is constant. The only thing changing is the number of moles of gas. So I can see I go from 1 mole of gas minus 0 moles of gas. So this increased by 1 mole of gas. Now, in this case, that is 0.25 moles, right? Because we can relate that. It's going to be 2.25 moles. Therefore, 0.25 moles of gas are being produced. So I'm going to plug in here 0.25. The molar gas constant is 0.082058 atmosphere liter per Kelvin per mole. The temperature has to be changed to Kelvin, so we're going to add 273.15, so this will be 298.15 Kelvin, and we'll use the 2 atmospheres. Okay, so that's just going to be 2 atmospheres, and that's going to result in 3.06 liters. Now, we got to change this to Pascal and meters cubed, okay, because that's going to be joules, okay? So again, when we have Pascal, meters cubed, that is equal to a joule. So that's why I had to convert it to Pascals in meters cubed. And again, that is going to be negative 0.618 kilojoules. So we lost 0.681 kilojoules of energy from the expansion of the gas. Okay, any questions about that? And you should know these conversions already. 1 atmosphere is equal to 101,325 Pascal, or 101.3 kilopascal. And then, of course, going from liters to cubic meters. The only conversion I know is 1 milliliter or 1 cubic centimeter equals 1 milliliter. So I'd have to take this to milliliters, convert the milliliters to cubic centimeters, and then the cubic centimeters to meters.
I have a question.
Yep.
Why do you transfer to these units?
To Pascal and meters cubed?
Yeah.
Because I'll add this to the slide. It won't affect you, but a 1 Pascal meter cubed is equal to 1 joule. It's just another conversion factor.
Okay,
What are the conversion factors for those?
For this part right here?
Yeah, like you have like P equals 2 atmospheres is equal to 2.2.
I just went through that, right? 1 atmosphere is equal to 101,325 Pascal. And then the liters to the meters cubed, again, I would have taken this to milliliters. 1 milliliter is equal to 1 cubic centimeter, and then from
Mhm.
cubic centimeters to cubic meter.
Okay.
Okay. And the only one that you're unfamiliar with is this, and I will add this to it. But 1 Pascal meter cubed is equal to 1 joule. Slide 14. Okay. Okay, so is everybody on board with me at this point? So we've calculated the work. This is the expansion work of this chemical reaction. Okay, next we have to calculate the heat. Well, we know that at constant pressure, again, this is all from Chem 110, at constant pressure, the heat is equal to the change in enthalpy. So, but a given temperature and pressure, we know a given amount of a substance has a definite enthalpy, which of course we can calculate in many different ways. We could actually measure it, measure the change in heat, knowing the heat capacity of the whole system. Or if everything is at standard conditions, we could simply use the summation law, right? Use the enthalpies of formation. And so that's what we're going to do. Now, these really are good at 1 atmosphere. Even though we have the 2 atmosphere in this problem, it's going to be close enough to use the enthalpies of formation. So these are the enthalpies of formation for standard conditions. That's what this little knot here means. 25 degrees Celsius, 1 atmosphere, 1 molar if we're talking about solutions, okay? And this is the summation law that we got in Chem 110. It simply says that the sum of the enthalpy formation of the products, and we'll talk more about what the enthalpy of formation and the enthalpy, the Gibbs energy of formation represent. Although, again, we covered all of that in Chem 110. You should go back and review what I asked at the beginning of these slides. But so the enthalpy of formation of the products, and enthalpy is an extensive property. So we have to multiply it by the number of moles within the balanced chemical equation. And then we're going to subtract from that the sum of the enthalpy of formation of the reactants, and again, each multiplied by the coefficient in the balanced chemical equation. The tables of chemical, the enthalpies of formation, of course, can be found in the tables of chemical data posted on Canvas or in the appendix of your text. And again, it's just the moles within the balanced chemical equation. And again, within the balanced chemical equation, those coefficients have units of moles, okay? So they do have units of moles. So basically, these are in kilojoules per mole. This is in mole. So the moles are going to cancel. So this will have units of kilojoules, not kilojoules per mole. Okay, this will have units of kilojoules. Okay, so let's do it then. We're going to look up in the tables, and we're going to look up the enthalpies of formation. And there they are. Okay, so again, we got these from the table. We'll plug that into the summation law. And we're going to get this, right? We have 1 mole of the calcium. Now I just dropped the units. I shouldn't have done that here, but I dropped the units. Okay, so it's 1 mole, and then this is negative 528 from the table, kilojoules per mole. There's 1 mole of water at negative 285.8 kilojoules per mole. There is 1 mole of carbon dioxide gas. Again, looked it up. It's negative 393.5 kilojoules per mole. So that's all of our products. We're going to sum them up, and then we're going to subtract from that the enthalpies of formation of our reactants. Well, there's 1 mole of the calcium carbonate at negative 1,207.6 kilojoules per mole, and then the enthalpy of formation of the hydrogen is 0, so that just cancels out. Plug that into your calculator, you're going to get a value of negative 14.5 kilojoules. Keep in mind, if you're following sig figs, you have mixed operations, but in this case, since we're multiplying everything by 1, each one is 1 digit past the decimal place, so our answer will be 1 digit past the decimal place. Now, this is for 1 mole of calcium carbonate, right? So we can make this a balanced thermochemical equation. So we would put a little semicolon here, and then write our thermodynamic value. In this case, our thermodynamic value is the change in enthalpy, but it could be the change in entropy, it could be the change in free energy. Whatever we calculate, we can turn this into a balanced thermochemical equation by putting a semicolon and then that value for the change in whatever that thermodynamic value is. What that allows us to do is relate this amount of energy to each of the reactants and or products. So in other words, when I react 1 mole of calcium carbonate, it's going to release 14.5 kilojoules of energy if the acid was in excess. If I reacted excess calcium carbonate with 2 moles of the acid, it would release twice as much. It would release 29 kilojoules of energy. So again, this is our balanced thermochemical equation. We'll have a molar energy ratio. So the molar ratio is where we related moles of one thing to moles of another thing within the chemical reaction. In a balanced thermochemical equation, we'll have the molar energy ratio, where we can relate the moles of anything in the chemical equation to the amount of heat that is released. So now we have this balanced thermochemical equation. We can determine the enthalpy change then for the reaction of 0.25 moles of the calcium carbonate with excess acid. So again, it'll be 0.25 moles. We want the moles to cancel, so the 1 mole of calcium carbonate will be in the denominator and the negative 14.5 kilojoules will be in the numerator. Again, this is our molar energy ratio, which comes from the balanced thermochemical equation. The moles of calcium carbonate cancel. And your final answer is going to be negative 3.6 kilojoules. So that is the amount of heat lost then in this reaction. So there it is. Now, because it's at constant pressure, we know that the change in enthalpy is equal to the heat at constant pressure. So now we know the amount of heat that was lost. We know the amount of work that was done. So the heat we just determined was negative 3.6 kilojoules. The work was equal to negative 0.618 kilojoules. So we simply plug that into Q plus W, and that gives us a total internal energy change of negative 4.2 kilojoules. So in other words, the chemical system, the chemicals themselves, lost 4.2 kilojoules of energy in this process. Now, again, if I just ignored the amount of work in this reaction where the work is actually significant for a chemical reaction, it still would only be an 11% error if I didn't include the heat. I'm sorry, I didn't include the work. Most of the energy in a chemical reaction is in the absorption or release of heat. Okay, but again, we don't want an 11% error, so in this case, we would have to include the amount of expansion work done by this system. Okay, so for this chapter, I'm going to go over some of the equations that you need to know and just kind of review some of the material as we go along. So first we talked about enthalpy, okay, and particularly we're going to talk about the enthalpy of formation. And the enthalpy of formation has the variable of del H, and then we have the subscript F, and then of course this little knot indicates standard conditions. So 25 degrees Celsius, 1 atmosphere, 1 molar when we start talking about solutions. And so an example would be, let's talk about the enthalpy of formation of a gaseous water. Okay, so the enthalpy of formation, and this is also going to hold true for the free energy of formation. So if we're talking about the enthalpy of formation or the free energy of formation, it is the amount of energy required to create 1 mole. So in the balanced chemical equation for an enthalpy of formation, again, each one of these, enthalpy of formation or change in entropy or change in free energy, always refers to some chemical reaction, okay? So, and again, it's always going to be for 1 mole of that particular substance. So, and it's going to be from the elements in their standard state. So how these elements exist in nature at 25 degrees Celsius, 1 atmosphere. Okay, so again, we're only going to have 1 mole of the product, and then whatever the elements are, which in this case are hydrogen and oxygen. So we have hydrogen and we have oxygen. Now the question is what does hydrogen look like in its elemental form? Hannah, what's hydrogen look like? How does hydrogen exist?
It's diatomic, so H2.
Absolutely. And what phase is it?
Gaseous.
Yeah, so if you look at the periodic table that you guys should be using for your exams and quizzes, you'll notice that the elements in red, well, in their standard state at 25 degrees Celsius in 1 atmosphere, they all exist as gases. The ones in blue, which are only bromine and mercury, they exist as liquids in their standard state. And then the rest of the elements you'll note are all in black, and that's because they exist as solids in their standard state. Then there's also the diatomics. So most of the elements can exist as a single atom by themselves. However, certain elements like hydrogen, nitrogen, oxygen, and the halogens, so fluorine, chlorine, bromine, iodine, and astatine, only exist as diatomics. Again, you need to know that. And the rest of them, again, can exist as monatomic atoms, so single atom by themselves. But again, the hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and astatine only exist as diatomic, so 2 of those atoms. So that exists as H2, and again, it is a gas. So Taylor, how's O2 exist then at 25 degrees Celsius, 1 atmosphere?
Would that just be O2 gas too?
Yeah, again, it's one of the diatomics, and we've seen that it was red on the periodic table. Now, because this has got to be fixed at 1, we got to change these coefficients so that it's balanced. So this is one of the few, in fact, this chapter, thermodynamics, is one of the few times where we actually have balanced chemical equations that have fractions in them, or can have fractions in them. Most of the time, we want the simplest whole number ratio for our coefficients. But in this case, we can't, and I'll show you why, because this is going to be forced to 1. So that's 2 hydrogen, 2 hydrogen. I have 1 oxygen, but I have 2 over here. So I only need half of them, right? So I only need half. So there would be the balanced chemical equation for the enthalpy of formation of gaseous water. Now, the amount of energy required to do that, well, that is going to be equal to negative 241.8 kilojoules. Now, when you look this up in the book, what you're going to find is that del F for gaseous water is equal to negative 241.8 kilojoules per mole. That's why this has got to be fixed at 1, because that per mole is for 1 mole of your gaseous, or whatever that product is, 1 mole of whatever that product is. This is a balanced thermochemical equation. So the mole disappears because it's for 1 mole of water, but now we can relate that energy to the 1 mole of hydrogen that's consumed, or the half mole of oxygen that is consumed. So again, this is that balanced thermochemical equation that we talked about yesterday, except I think we were referring to it as in terms of free energy. But again, any thermodynamic value can go here. And then we're going to relate that amount of energy to the coefficients in the balanced chemical equation, just like we did for normal molar ratios, where we just related the moles of reactants and products to one another. Okay, now the enthalpy of formation of liquid water, on the other hand, is different. So again, this would be for 1 mole, because it's always 1 mole, of liquid water. Now this side's going to be the same because it's still hydrogen, okay, and hydrogen exists as a diatomic and it's a gas. It still consists of oxygen, so that's O2, and it's a gas. And again, to balance it, we have 1 oxygen, so we only need 1 of these 2, so that would be 1/2. But this time, the enthalpy of formation is not equal to the 241.8, but equal to negative 285.8. Okay, and well, why is that? Well, because we know if we want to evaporate water, right? If we want to go from the liquid to the gas, we actually call that the enthalpy of what? When we go from a liquid to a gas, what do we call that, Keenan?
Oh my gosh, I'm blanking here. Give me a second.
Sure.
I can see it, I just can't remember it. I'm sorry.
That's okay. So it's vaporization, right?
Yes, thank you.
So vaporization. So this would represent the enthalpy of vaporization. And for water, that would be equal to 44 kilojoules per mole. But in this case, again, because the mole is represented here, we just say 44 kilojoules. Okay. So if we're going, again, from the liquid to the gas, you can see that we would add 44 to this number, which would make it negative 241.8. So this is why the phases are so important when we talk about the enthalpies of formation and later on the free energies of formation. Okay. Okay, any questions about enthalpies of formation? Okay, so, and again, note that we can put any of the thermodynamic values here, enthalpy change, free energy change, or entropy change. And again, they would all be related to the coefficients in the balanced chemical equation. So let's just try an example here. So let's look at methane. So methane, the combustion of methane, so methane reacting with some oxygen to produce carbon dioxide and water vapor, okay? And if we wanted to calculate the enthalpy of this reaction, we could use the enthalpies of formation, okay? And of course, the enthalpies of formation is just going to be the change in enthalpy. And again, these are going to be under standard conditions because all of these enthalpies that are in the back of the book, okay, or in the tables of chemical data are all under standard conditions. So 25 degrees Celsius in 1 atmosphere. And that's just going to be equal to then the sum of the enthalpy of formation of the reactants, the products. And again, since it's an extensive property, we got to multiply each by the coefficient in the balanced chemical equation. And then we're going to subtract from that the enthalpy of formation of the reactants. And again, we'll have to multiply each of those by the number of moles, so the coefficients in the balanced chemical equation, okay? So what we do next then is we simply are going to look up the enthalpy of formations in the tables of chemical data or the appendix of your book. And so for gaseous methane, that's negative 74.6 kilojoules per mole. Again, if you understand what's going on with the enthalpies of formation, I recognize right off the bat, O2 gas, that is the way that element exists at 25 degrees Celsius in 1 atmosphere. So again, it doesn't take any energy to create O2 gas from O2 gas, therefore it would be 0. Now, anything that has more than one element in it can't be 0. Okay, it's going to have some non-zero value. So we're going to look up carbon dioxide gas, and it is negative 393.5 kilojoules per mole, and gaseous water at negative 241.8 kilojoules per mole. So we're going to simply plug that into this guy here. So that is going to be our products. So there's 1 mole of CO2. So 1 mole, this is for CO2, at negative 393.5 kilojoules per mole. We'll add to that the 2 moles of gaseous water at negative 241.8 kilojoules per mole. Now that was all of our products. Now we're going to subtract our reactants. So we have the 1 mole of methane at negative 74.6 kilojoules per mole. And then the 2 moles of O2, but that's at 0, right? So that's at 0 kilojoules per mole. So that term just kind of cancels out. So then this then is going to equal, so this is going to equal, and again, remember you have mixed operations here. So basically the moles cancel the whole way through. So we're just going to have units of kilojoules now. And so we're going to have negative 393.5 and then plus, which now is going to be negative, right? So it'll be negative, and then we have to multiply that by 2. So that's going to be 483.6. Whoops, these are kilojoules. Now this was 4 sig figs, so this has to be 4 sig figs, so that'll put it there. And then we're going to subtract from that this value here, which is negative 74.6 kilojoules. Plug that into your calculator, and that's going to be negative 802.5 kilojoules. So now all we're doing is adding and subtracting. This is 1 past 1 past 1 past the decimal, so the answer will be 1 past the decimal. And so your enthalpy for this reaction then would be 802.5 kilojoules. Okay. Then of course we could turn this into a balanced thermochemical equation by simply saying del H equals negative 802.5 kilojoules. Now I could relate this energy to any of the coefficients in the balanced chemical equation. Whoops, any of the coefficients in the balanced chemical equation for my energy molar ratio. Okay,